A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. So Daniel sent us this one, and I'll read it out. He's asking about a growing counter-narrative in AI engineering. The argument that most multi-agent systems are over-engineered solutions to problems a single well-prompted agent could handle better. He points to Karpathy arguing that multi-agent frameworks add coordination complexity without proportional benefit. Anthropic's own team saying most multi-agent setups are better served by a single agent with good tool use. Harrison Chase, the founder of LangChain, acknowledging that single agent with tool use covers 90% or more of use cases, and Simon Willison consistently arguing that simpler approaches beat elaborate orchestration. On the empirical side, he's citing Google DeepMind's December 2025 study of 180 agent configurations, which found independent agents amplify errors 17.2 times versus 4.4 for centralized coordination, and sequential reasoning degrading 39 to 70% in multi-agent setups. Daniel wants us to dig into where the line actually is, and whether the bar for reaching for multi-agent should be dramatically higher than current hype suggests.
Herman Poppleberry here, and I want to say up front, this is one of those topics where I think the research is actually ahead of the discourse. Most of the coverage is still in multi-agent is the future mode, and meanwhile the people who build these systems for a living are quietly publishing some fairly damning evidence.
Right, and what I find interesting is who is saying this. It's not critics on the outside, it's Anthropic's own engineering team. It's the founder of LangChain, a company whose entire commercial existence depends on people building complex agent systems. When the person selling you the framework says, you probably don't need this, that's worth paying attention to.
Harrison Chase's post is remarkable for exactly that reason. He's essentially writing a piece that, if taken seriously, would reduce his addressable market. And his framing is actually quite precise. He says context engineering is the #1 job of engineers building AI agents. Not orchestration, not spinning up agent fleets. Managing what context each agent call receives.
Before we get into the empirical data, I want to make sure we're clear on what the actual claim is, because I think it gets muddied. Nobody credible is saying multi-agent is useless. The claim is that the bar for using it should be much higher than the current hype suggests.
That's the right framing. And it's the framing both Anthropic and cognition use. Anthropic's Building Effective Agents Guide, written by Eric Schluntz and Barry Zhang, opens with something that should have been a headline, consistently. The most successful implementations weren't using complex frameworks or specialized libraries. And then it goes further, we recommend finding the simplest solution possible and only increasing complexity when needed. This might mean not building agentic systems at all.
That last sentence, this might mean not building agentic systems at all, from Anthropic.
From the people who build Claude, which is running inside most of the agent frameworks people are using. And the cognition post, Walden Yan's Don't Build Multi-Agents from June last year, is even more direct. Cognition builds Devon, which is one of the most sophisticated coding agents in production, and their recommendation is don't do what we did unless you have very specific reasons.
By the way, today's script is powered by Claude Sonnet 4.6, which I find slightly ironic, given that we're about to spend 25 minutes arguing that you probably need fewer AI systems, not more.
The recursive self-awareness there is not lost on me.
Okay, so let's get into the Google DeepMind study, because the numbers are striking. 180 agent configurations across 5 architectures and 4 benchmarks. Walk me through what they actually found.
So the study, RX525 wall to 8296 published in January of this year, is the most comprehensive empirical treatment of this question I've seen. They tested 5 coordination architectures: single agent, independent parallel agents with no communication, centralized hub and spoke with an orchestrator, decentralized peer-to-peer mesh, and a hybrid, across 3 LLM families and 4 benchmarks including financial reasoning, web browsing, planning, and general task completion.
And the headline finding is that it depends enormously on task type.
Enormously. On parallelizable tasks, they use financial reasoning as the example. Centralized coordination improved performance by 80.9% over a single agent. That's real. That's not noise. But on tasks requiring strict sequential reasoning, like the planning benchmark PlanCraft, every multi-agent variant they tested degraded performance by 39 to 70%. Every single one. And the mechanism is important. The overhead of communication between agents fragmented what the researchers called the cognitive budget, the available reasoning capacity for the actual task.
So you're spending tokens on coordination that you could be spending on thinking.
Which the Stanford paper then formalizes mathematically. Tran and Duekiela at Stanford, paper published April 2nd this year, use information theory to explain why this happens. The data processing inequality says that when you pass information through an intermediate step, you can only lose information, never gain it. So when you split reasoning across multiple agents, each agent sees a subset of the full context. The handoffs necessarily lose information. A single agent with the full context is information, theoretically guaranteed to perform at least as well.
That's not an empirical result you can argue with. That's a mathematical constraint.
And the empirical results confirm it. They tested across Qwen 3, DeepSeek R1 Distill Llama, and Gemini 2.5 across 5 multi-agent architectures including sequential, parallel, debate, and ensemble setups. Single-agent systems consistently match or outperform multi-agent on multi-hop reasoning when you hold the token budget constant.
And that's the key phrase, when you hold the token budget constant. Because the Stanford paper also identifies what might be the most important methodological point in this whole debate.
The token confound. This is the part that I think should genuinely embarrass a lot of benchmark authors. Most reported multi-agent performance gains in the academic literature are confounded by unequal computation. Multi-agent systems use more tokens, sometimes dramatically more, and researchers don't normalize for this. When you control for total tokens consumed, single agent matches or beats multi-agent. The apparent architectural advantage evaporates.
So the benchmark is essentially comparing a single agent on a fixed budget versus a multi-agent system that gets to spend more, and declaring the multi-agent system smarter.
Which is not a fair comparison. The Stanford paper is quite direct about this. Many reported advantages of multi-agent systems are better explained by unaccounted computation and context effects rather than inherent architectural benefits. That's a strong claim from a peer-reviewed paper. And Anthropic's own multi-agent research post corroborates it. They found that token usage alone explains 80% of performance variance on their BrowseComp benchmark.
80%. So most of what looks like better architecture is just more tokens.
And here's the corollary that I find really striking. Anthropic also found that upgrading to a better model, going from Claude Sonnet 4 to Sonnet 4.7, was a larger performance gain than doubling the token budget. So the right answer to my agent isn't performing well enough is probably use a better model, not add more agents.
Which brings up the error amplification numbers from the DeepMind study, because this is where the cost of getting the architecture wrong becomes very concrete.
The error amplification finding is the one I keep coming back to. Independent multi-agent systems, agents working in parallel without communicating, amplified errors by 17.2 times compared to a single agent. Centralized systems with an orchestrator contained that to 4.4 times. So an orchestrator helps, but you're still multiplying your error rate by 4+. The orchestrator acts as what the paper calls a validation bottleneck. It catches errors before they propagate, but it can't eliminate the underlying fragmentation problem.
And the cognition team's Flappy Bird example illustrates exactly how this plays out in practice. You build a Flappy Bird clone into parallel subtasks. Subagent 1 decides to build a Super Mario Bros. Background. Subagent 2 builds a bird that doesn't match. The merging agent is now left reconciling two independent decisions that were never coordinated.
Walden Yan's framing of this is, actions carry implicit decisions, and conflicting decisions carry bad results. Every agent call is making assumptions about what other agents will do. In a single agent system, those assumptions are internal and consistent. In a multi-agent system, they're distributed and potentially contradictory.
This is also what cognition calls the context engineering problem. The argument is that the real skill isn't orchestrating agents, it's ensuring each agent call has exactly the right context. And splitting context across multiple agents is often the wrong solution to a context management problem.
Chase uses the same framing independently. He calls context engineering the #1 job of engineers building AI agents. And both he and cognition arrive at the same conclusion. Read. Heavy tasks are more naturally parallelizable than heavy tasks. When you're doing research, pulling from multiple independent sources simultaneously, parallel agents are a reasonable fit. When you're synthesizing or writing, splitting the work creates incoherence.
And Anthropic's own multi-agent research system is actually a perfect illustration of this principle in practice. They built a multi-agent system for research, and even in that system, the actual writing, synthesizing findings into a coherent report, is deliberately handled by a single main agent in one unified call.
That detail is buried in their engineering post, but it's really important. The multi-agent part handles reading and information gathering. The single agent part handles writing. They drew the line exactly where the theory says to draw it. Parallelizable information retrieval, multi-agent. Sequential synthesis requiring unified context, single agent.
So even the pro-multi-agent post from Anthropic is essentially an argument for very careful, bounded multi-agent use.
And the cost numbers they publish make the economic case even clearer. Single agents use roughly 4 times the tokens of a standard chat interaction. Multi-agent systems use roughly 15 times. That's 3.75 times the token cost of a single agent just for coordination overhead. Anthropic's framing is direct. For economic viability, multi-agent systems require tasks where the value of the task is high enough to pay for the increased performance. Most enterprise use cases don't clear that bar.
Let me push on the Karpathy angle here, because his position is more nuanced than I initially read it. His auto-research experiment, 700 experiments in 2 days, is actually a single-agent system. And yet his vision for where this goes is very much about agent swarms.
Right, and this is where I think Karpathy's view is actually the most sophisticated of the bunch. He's not anti-multi-agent, he's arguing for the correct order of operations. His auto-research system, a single agent continuously improving a piece of code along one path, proved the concept first. And then his articulation of what comes next is specific. The next step for auto-research is that it has to be asynchronously massively collaborative for agents. The goal is not to emulate a single PhD student, it's to emulate a research community of them.
But notice the use case. He's talking about parallel optimization of machine learning training runs, genuinely independent experiments that don't need to share context. Spin up a swarm, have them explore different optimization paths simultaneously, promote the most promising ideas to larger scales. That's a task structure where multi-agent is theoretically well matched.
And there's an interesting community observation about his work that captures a real phenomenon. The bottleneck shifted from can the agent do this task to can we coordinate across 6 agents without creating chaos. The agents got better faster than the coordination architecture did, which means multi-agent systems that were designed for weaker models may now be actively harmful when used with frontier models.
That's the DeepMind paper's capability saturation finding, right? Coordination yields diminishing returns once single-agent baselines exceed certain performance thresholds.
The paper puts it plainly, as models get smarter, the case for multi-agent gets weaker, not stronger, which is counterintuitive relative to how most people think about it. The assumption is that more capable models would be better at coordinating with each other. But what actually happens is that a single capable model needs less help, so the overhead of coordination becomes a larger fraction of the cost with less offsetting benefit.
So the advice for someone using a frontier model today is essentially, the threshold for reaching for multi-agent is higher than it was 18 months ago, not lower.
That's the right read. And the DeepMind paper actually developed a predictive model for this, R squared of 0.513 that correctly identifies the optimal coordination strategy for 87% of unseen task configurations using just two measurable task properties, tool count and decomposability.
Two variables. That's a remarkably simple decision rule.
It is high tool count and low decomposability, single agent. Low tool count and high decomposability, multi-agent. The tool count finding is particularly interesting. As tasks require more tools, the coordination tax of multiple agents increases disproportionately. A single agent managing 16 tools is more efficient than multiple agents, each managing a subset.
Okay, so let's build the actual decision framework, because I think this is what most listeners are going to want to walk away with. When should you actually use multi-agent?
The evidence converges on a fairly clear set of conditions. First, genuinely parallelizable tasks where independent subtasks can be explored simultaneously without needing shared context. Breadth-first research is the canonical example, multiple agents pursuing different information threads at the same time, with a single agent synthesizing at the end. Second, tasks that genuinely exceed a single context window where the information required cannot physically fit in one call. Third, very high-value tasks where the 15 times token cost is economically justified by the output value. Fourth, situations where you specifically need genuinely independent perspectives, negotiations, competitive simulations, red teaming.
And the conditions where you should stay single agent?
Sequential reasoning. The 39 to 70% degradation is not a small effect. Coding tasks, because most coding work involves more dependencies than people realize and is less parallelizable than research. Writing and synthesis for the same reason. Conflicting implicit decisions from parallel agents create incoherent outputs. Tool-heavy tasks. And perhaps most importantly, when you're already using a frontier model. The capability saturation effect means the case for multi-agent weakens as your single-agent baseline improves.
There's also a debugging dimension that I think gets underweighted in these discussions. Multi-agent systems are dramatically harder to debug. When something goes wrong in a multi-agent pipeline, the error could have originated in any of several agents, been transformed at each handoff, and arrived at the output in a form that's disconnected from the root cause.
Anthropic's Building Effective Agents guide is actually quite pointed about this with respect to frameworks. They warn that frameworks often create extra layers of abstraction that can obscure the underlying prompts and responses, making them harder to debug. They can also make it tempting to add complexity when a simpler setup would suffice. Coming from Anthropic, that's a pretty direct critique of the ecosystem that's built up around their own models.
I want to come back to something Simon Willison said, because his framing of when to design an agentic loop at all is the most conservative of the bunch, and I think it's worth sitting with. He says the thing to look out for is problems with clear success criteria, where finding a good solution is likely to involve trial and error. That's a very narrow definition.
And his eventual embrace of parallel coding agents comes with an important constraint. He says he can only focus on reviewing and landing one significant change at a time. So even when he runs parallel agents, he's doing it for research and proof of concept work, read-heavy or low-stakes write operations, not production code.
The read-write distinction keeps coming up from every direction. Research, multi-agent can help. Writing, single agent almost always wins.
It maps cleanly onto the information theory. Reading is pulling in information from independent sources. The sources don't need to know about each other. Writing requires a unified internal model of what's being produced. Splitting that model across agents introduces incoherence.
Let me ask the uncomfortable question. Given all of this, the empirical data, the expert consensus from practitioners, the information, theoretic argument, why is multi-agent still the dominant narrative in the industry?
A few factors. One is that the benchmark results, before the token confound is corrected for, genuinely showed multi-agent winning. The Stanford paper only came out this month. The methodological problem was hiding in plain sight, but nobody had formally exposed it at scale until now. Two is that multi-agent is a more exciting story to tell. We built a team of AI agents that collaborate is a better demo than we wrote a really good system prompt. Three is that frameworks have commercial interests. LangGraph, AutoGen, Crew AI. Their existence depends on people building complex agent systems. The fact that Harrison Chase wrote a post acknowledging single agent covers 90% of use cases is genuinely unusual.
And there's probably a selection effect in who publishes. If you built a multi-agent system that outperformed a single agent, you write a paper. If your single agent just quietly solved the problem, you ship the product.
Publication bias is real. The DeepMind study is important partly because it's one of the few large-scale empirical studies that tested both directions and found conditions where single agent wins.
What's the practical takeaway for someone who's currently building an agent system or planning to?
The first question to ask is whether the task is actually decomposable into genuinely independent subtasks. Not could I theoretically split this, but do these subtasks actually not need to know about each other? If they do need shared context, multi-agent will hurt you. The second question is whether you're already using a frontier model. If yes, the capability saturation effect means your single agent baseline is probably higher than you think, and the case for multi-agent is weaker than it was when you last evaluated it. The third question is the economic one. Can the value of the output justify roughly 15 times the token cost of a standard interaction?
And if you fail any one of those three tests, the default answer is single agent with better context management.
Anthropic's framing is the most useful here. For many applications, optimizing single LLM calls with retrieval and in-context examples is usually enough. That's not a concession. That's the actual finding from production systems. Context engineering, getting the right information into a single well-designed agent call, is the skill that moves the needle most of the time.
The Cognition team makes a related point about Claude Code specifically, which I find revealing. They analyzed Claude Code's architecture and found it never does work in parallel with a subtask agent, and the subtask agent is usually only tasked with answering a question, not writing code. The designers of one of the most capable coding agents in production took a purposefully simple approach.
And Claude Code is the product that's actually changing how developers work at scale, not because of architectural complexity, but because of extremely careful context management within a relatively simple agentic loop.
So the meta lesson might be, don't let architectural ambition substitute for context engineering discipline.
That's it. The question, how do I coordinate multiple agents, is often the wrong question. The right question is, what does this single agent call need to know, and how do I make sure it has exactly that?
What's the open question you're most interested in watching?
The capability saturation effect, honestly. The DeepMind paper found that as single agent baselines improve, multi-agent coordination yields diminishing returns. We're in a period of rapid model improvement. If that finding holds, and if models continue improving at anything like the rate of the past 18 months, the set of tasks where multi-agent is the right answer might actually be shrinking rather than growing. Karpathy's vision of agent swarms for parallel ML optimization might represent the in-game use case, a narrow, specific problem class where the architecture genuinely fits rather than a general paradigm.
Which would be a pretty significant reorientation of where the industry thought it was going.
It would. The assumption has been that we're in an early phase of multi-agent and coordination architecture will catch up. The alternative reading of the data is that single-agent capability is outrunning the coordination problem, and the window where multi-agent was the best answer for most tasks may already be closing.
That's a genuinely interesting place to leave it. Big thanks to our producer Hilbert Flumingtop for keeping things running, and thanks to Modao for the GPU credits that power the show. Genuinely couldn't do this without them. If you want to find us, search for My Weird Prompts on Telegram, and you'll get notified when new episodes drop. This has been My Weird Prompts. We'll see you next time.
Later.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We shake.